welcome to this episode of Gov School Rocks, where we spend some time trying to learn to speak rock and trying to learn to listen to what the environment is telling us. Today we're going to look at minerals. When we think about building the story of our planet, we got to think about the basic building blocks of things. If we think of the story of our planet like a book or like a series of books, we can think of minerals as the individual words and rocks as the individual sentences or even paragraphs. Minerals, which you probably learned about back in earth science, perhaps in 8th or 9th grade, are the building blocks of rocks. Minerals have a particular definition. They're naturally occurring. So minerals we make in labs and or in industrial processes don't count as minerals, even if they may have the same crystal structure and physical properties as a mineral like this quartz here, or amethyst. They're still not minerals. So minerals are naturally occurring, inorganic, meaning that they're not produced through or produced as biological processes. They can be produced by biological organisms, like for instance, the crystals that make up the aragonite and calcite crystals that make up shells in pelecypods, also known as bivalves, also known as clams. Or the minerals that make up your tooth enamel, the hydroxyapatite or apatite, calcium phosphate, which is secreted by your body for bones and for tooth enamel. That's still a mineral itself, but as much as coal is not a mineral, nevertheless, there is a sort of gray line with the inorganic question. Minerals are solids. So we can't have a liquid or a gas or a plasma, let alone a plasma. So they're solid. That's pretty straightforward. That's a particular state of matter that you're familiar with. So naturally occurring inorganic solid. All right, with a definite chemical composition. This is amethyst. It's a variety of quartz. Quartz comes in a lot of varieties, basically related to the color and the impurities that lead to those colors. So this purple amethyst, which two places where you can find this would be some places in Brazil, and then north of Lake Superior. This particular specimen, I'm not sure of its original provenance, but quartz is made up of silicon and oxygen in the form of silicon dioxide, little molecules that come together to form what we call silicon tetrahedra, where there's a single silicon atom surrounded by oxygen atoms in a sort of triangular shape. That chemical formula is unique to all quartz. All quartz is silicon dioxide. That chemical formula leads to a particular crystalline structure, and that's the next part of the definition. So naturally occurring inorganic solid with a definite chemical composition and crystal structure. The crystal structures, though, can vary a little bit within that chemical composition. So, for instance, quartz doesn't have a lot of variety in terms of its in terms of the crystal structure, but a mineral like this calcite over here, all right, this is calcium carbonate, and that's a particular chemical formula and a particular crystal structure. But I can also have varieties of this called aragonite that are also calcium carbonate. They have a different crystal structure. Those are called polymorphs, where a particular crystal structure can come in a variety of shapes, many shapes, polymorph, if you know your Greek. So naturally occurring inorganic solid with a definite chemical composition and a crystal structure, and then I like to add distinctive physical properties. Some of those physical properties are things that are easy to test. Can I scratch it with my fingernail? Can I scratch it with a steel knife or a steel blade or a nail? These are things that test relative hardness. And relative hardness is on a scale of 1 to 10. You've heard of it, Mohs hardness scale. That's different from absolute hardness. Diamonds are absolutely way harder than the next mineral down than a 9, like corundum. So absolute hardness scale is actually exponential, while the relative hardness scale is arithmetic. So it's, or at least if I think about functions that kind of mirror that, that's what I would think of. Other things include streaks and streak plates, which are unglazed ceramic tiles, the color of the streak. You might think of the color of the mineral as diagnostic, but as we spoke about quartz here, color isn't terribly useful when you're looking at something like this, because Quartz can come in a variety of colors and still be quartz. Other diagnostic physical properties include things like, or chemical properties in this case, but we're going to refer to it that way, is like things like the effervescing of the mineral when you drop acid on it. So if I put acid on this calcite, you'll see it fizzes. You may be able to see that pretty well from where you are. Okay, there it effervesces. If I did the same thing with quartz or other minerals that don't react that same way with hydrochloric acid, you wouldn't see that. So there's physical properties we use to help identify minerals. Another one of those physical properties includes something called cleavage or fracture. So some minerals cleave in particular ways and in particular directions. This is muscovite, really nice big chunk of it. And I was able to cleave using this knife here, a sheet of it off, because this is a silicate mineral. So at its basic structure, it's based off of the silicon tetrahedra. It's not SiO2. It's a much more complicated mineral than that. But because of its crystal structure, it cleaves off in perfect sheets. So we call this perfect cleavage. All right. And you can see there's another physical property in this mineral, in that as I put it up to the lens, you can still see through it. So its translucence is also a physical property, whether light can pass through it or be reflected by it, which is luster, yet another physical property. Okay, to wrap things up, I'm going to show you a rock. This rock came from Timberville, Virginia, not far from where any of you live. And you can see in it several colors. You can see this gray, this limestone. You can see the white, calcite. And you can see this yellowish brownish mineral, the sphalerite, which is the mineral of interest for those people who were mining for zinc back in the 50s in Timberville. This comes from a place called what used to be called the Bower Campbell Zinc Mine. So this rock was formed originally as a part of an ancient marine basin, an ancient seabed where the limestone formed from the deposition of little marine microorganisms, microplankton, foraminiferae, and so forth once they died. This was all gray limestone at that time, or mud, which turned into limestone. The formation of the Alleghenian, or the Alleghenian orogeny forming the Allegheny Mountains, eventually led to the brecciation, or the breaking of this limestone up, folding on large scale and faulting. But in small places along there, you have the breaking up of the rock. During that mountain building event, 248 million years ago, and part of that brecciation within the interstices, or the gaps, the pore spaces, was able to flow calcium carbonate rich water, which eventually left behind calcite crystals, as well as other minerals, sulfate minerals. In this case, we have zinc sulfide, sphalerite, which we use for galvanizing steel and nails and things like that. Also use it in, you can get the zinc out, you can separate the zinc out and use it as a supplement. You can use it in paints, you can use it in cosmetics and so forth. Lead sulfide, or galena, can also be found in this particular ore, as well as sometimes pyrite, iron sulfide. These minerals are all moved through here hydrothermally. Of course, they were in place many millions of years ago at this point. So sometimes they're enriched in certain places, and we call those ore bodies, or bodies of rock that are economical to mine for particular minerals. Okay. The bottom line here, though, is before we talk about rocks in subsequent videos, is that minerals are the building blocks of rocks. I just gave you a story of this rock. Okay, we could go on and talk about how it's a Mississippi Valley type deposit for zinc ores and things of that nature. But this rock, the complexity of the mineralogical complexity of this rock gives it its story. And we can interpret that if we learn how to speak its language. So that's it for this episode. In the next episode, we're going to talk about igneous rocks, the most primal of all of them. See you then.